The topic of this video is entropy transfer. And in order to form a quantitative form of the second law, unlike the qualitative forms of the Clausius and Kelvin-Planck statements, we have to consider the entropy that is transferred associated with all forms of energy transfer. And that'll be namely the entropy transfer associated with work, heat transfer, and mass transfer across boundaries. The first type of energy transfer that we're going to look at is work, and to do so, we're going to take a control volume and we'll assume that this has a mass contained within it and that it's existing in a vacuum so that there's no other influences other than the fact that we have a small massless string that is able to raise and lower the mass by imparting a differential amount of work, delta W. So to look at the entropy change, ds, of the system when we do some work on it, we're going to start with Gibbs' equation. Now in this case, we've assumed that this is a slow process with negligible friction, or it could be existing in a vacuum, in such a way that there's minimal change in the internal energy of the system when we raise the mass by this massless string. So we cross off that term. Additionally, we assume that there's no change in volume in this case because the work is simply causing a change in potential energy. There's no other influences that would be changing the volume of anything within the system, and so we can also cross that term off. So just to recap our justifications in the simplifications of Gibbs' equation, we said that the change in internal energy is negligible because we're assuming that even if this is not in a vacuum, if it has a medium around it, the process is at least slow enough that friction and mixing are negligible and there's no increase in internal energy as a result. And similarly, we're assuming that the dV term goes to zero because the delta W, the small amount of work that's done, goes directly into increasing the potential energy of the system and nothing else. So at the conclusion of all this, we can say that based on Gibbs' equation, we can conclude that the change in entropy due to work crossing the boundary is zero. Now for this simple example, we just used a mass on a string, but you may be wondering, how about PdV work? So from the first law, we know that the delta W is just going to be equal to du for a closed system, and that the magnitude of the work is going to be minus p dv, assuming the system does the work on the surroundings. And then if we go back to the Gibbs equation where we have ds, we've got the first term is a du, so we have, again, this expression here is giving us what our du is, and it's going to be negative, so we'll have negative p dv over t. And then the second term in Gibbs' equation is p dv over t. So again, in this case as well, the change in entropy of the system when you do p dv work is also zero. So to conclude our discussion of entropy transfer by work, we conclude that there is no entropy transfer associated with work. And it's worthwhile to note that the case where the string was cut and the mass fell to the ground, we would have the energy transfer from potential energy to kinetic energy, ultimately to internal energy, as we discussed when we were looking at the first law. And this would indeed cause an increase in entropy because the du term would be non-zero and in Gibbs' equation, and we would have a ds. So the next thing that we're going to look at is the entropy transfer associated with heat transfer. And so to do this, we've just defined a system and a control volume that's sitting at a certain temperature, and we have the transfer of heat only. We'll assume for this case it's only heat, and then there's no work being done. So if we go to our Gibbs equation, so we will use the same Gibbs equation that we used before. So we have ds is equal to du over t plus p over t dv. We said there'll be no pressure volume work, so we'll just cross off the dv part just to look at the heat transfer part only. Then we need to use the first law in order to figure out what delta U is, and we just get delta Q minus delta W is equal to dE. If we can neglect the effects of changes in kinetic and potential energy, the dE is equal to du. We've stated previously that we're going to look only at heat transfer and not look at the impact of work, so we'll cross that one off. And we just end up with delta Q equaling du. We can then take that back to Gibbs' equation and say that ds is equal to delta Q over T. Okay, so we can conclude that this expression here gives us the entropy transfer that is associated with the heat transfer, where the heat transfer has a magnitude delta Q, and we note that the temperature at which the transfer happens, so the temperature of the system or its boundary, is important in defining the entropy change. So the third and final entropy transfer that we want to look at is that associated with mass, specifically mass crossing the boundary. And so this is the system that we're going to be looking at. So we have defined a little parcel of mass with mass delta M, and the entropy, the specific entropy of that little parcel is S. And then we look at what happens when that parcel fully crosses the boundary of the system. So as I mentioned, the parcel of fluid we're talking about has a specific entropy S associated with it. And when the parcel is moved across the boundary, essentially it takes its entropy with it. And so if the mass flow rate across the boundary is m dot, the rate of entropy transfer across the boundary is going to be m dot S, expressed through this equation. Now, since there's no entropy transfer associated with work, there's also no entropy transfer associated with the flow work that's required to cross the boundary. And so this is all that we have to take into account. We don't have to do anything with the fact that there's flow work in addition. Okay, so that summarizes the three main entropy transfers that we can see in a system, which will allow us to develop our quantitative form of the second law.